the first thing I would like to discuss myself, it's from the previous list. Yes, and also Sanchita asked, hopefully she will come, Sanchita asked how to compute angles between roots corresponding to SLN. So she needed this for the first problem in the seventh list of problems, right? So this is all related. So, but first, how to see that SL3 with Cartan subalgebra corresponding to diagonal traceless matrices. How to see that this and we have corresponding root system, right? How to see that this is exactly A2? Well, to see that this is exactly A2, it's pretty simple. We just can count roots, right? So what are the roots? So first of all, let's recall what are the roots of SL, just SLN even.
It's E sub I minus E sub J.
Yes, so what is E sub I? So it just, I think you was discussing this, right? So it just, well, I have diagonal matrix, right? Like this, N, right? And then the value of E epsilon, I don't know, maybe E, let's call it this epsilon, is just gives me HI. So this is the definition of an element epsilon I in H star, right? And we have N of them, but well, this is an element not in H star. Well, it is an element in H star, of course, but these elements together, they do not form a base, right? Because the dimension of H star is n minus 1. So I actually would like to have a basis. So in particular, epsilon I minus well, anyways, so what are the roots of SLN? The roots are like this: epsilon I minus epsilon J, right? So root system corresponding to this. This is a reminder, right? Where I is not equal to J. So we can now take this and count how many roots are in this root system, right? So we have epsilon 1 minus epsilon 2, right? Epsilon 2 minus epsilon 3, and epsilon 1 minus epsilon 3, right? And plus or minus. Each of them. So we have 6 roots. So if you look at the pictures that we had last time, the only picture which has 6 roots is A2. It has this root, again, our favorite picture. So this has exactly 6 roots corresponding to these numbers. Now, how to compute angles and check that they actually correspond? Well, first of all, let me take pluses here, right? So I need to choose, if I choose epsilon 1 minus epsilon 2 to be alpha 1, and then epsilon 2 minus epsilon 3 to be alpha 2, and then this one is alpha 1 plus alpha 2, it's alpha 3. right? So just from this relation, we can take any three vectors that lie in one half plane, this three or this three, but by standard it's just this three, and claim them to be alpha 1, alpha 2, and alpha 3. So this is already just from linear relations and number of roots. We already see that this picture, because these things, all right. We now can go further and check that root angles are those that we need. And for angles, we can do the following. We can take trace form. So this is x, y. So x and y, they are in SL3, right? Of course, we computed angles with Killing form by default, right? But we know that SL3 is simple, and then therefore Killing form is just a multiple of trace form, and we actually know exactly which multiples. 2 times 3 in this case, or 2n for SLn, right? Yes. So how to compute now, for example, this? Just we need to recall by definition, this is this trace form of H capital alpha 1 and H capital alpha 2, right? Now I can think of the following. So if I have so H is diagonal traceless matrices, and let me just introduce all diagonal matrices. Just it will be useful. Right. Then then I have the following. Right, so then this form, trace form, is still non-degenerate on D, not only on H, but on D as well, right? And then I can define for any epsilon, I can define corresponding H epsilon I, right? So I would like to introduce this D because this, well, anyways, you can think of it as in D, so this is, well, it doesn't really matter. You can, this is in D star and this one is in D, right? So what is H epsilon though? I. So by definition, yes. So the answer is that this is E I. Okay. So how to see that? So what was the definition? Is that if I take epsilon I and compute it on some element H, right, from H star, then this is the same as taking H epsilon I without star. Sorry, you're right. H epsilon I with this H. So this is definition of H epsilon, right? So I need something, right, some element, such that if I compute its trace form with any H, it gives me ith entry on diagonal of H, right? You can just check that it is exactly EII. So the trace of EII, you can see the trace of EII, jj is delta ij. Right? So therefore, it means that trace of ei with any h from h is hi. Right? Just decompose hi as a sum of ejj's, right? And the only the one that survives is ei. So therefore, h epsilon is exactly epsilon I is ei. But then how to compute this? So this will be trace of ei 1, right, in this case. E11 minus E22, right, times E22 minus E33, right? So this is what? So this is trace of the following: 1 minus 1, 0, 1 minus 1, 0. So if I multiply them, right, I will get negative 1 in the middle and zeros here, right? So the trace is negative 1. To compute an angle, I will need to compute alpha 1, and alpha 2, right? Then the cosine will be what? Cosine will be negative 1 divided by the product of these two, right? Because, so let me see. So alpha beta is alpha beta times cosine of phi, where phi is an angle between them, right? So I need to divide this by square root of the product of these two, right? Okay, so if I take this, I have to compute trace of the square of this. So it's trace over 1, 1, 0. 1 plus 1, 2, so it's 2, right? So this thing is 2. This thing is 2. How this is 2, right? So I need to trace. So h, right? So let us do this in better way. So let's compute alpha 1. It is by definition h, well, e, right? It's h e epsilon 1 minus epsilon 2, h epsilon 2 minus epsilon 3, right? So these things are E11, so I have to compute trace of E11 minus alpha 1 here, so it's the same, right? So trace of this thing squared, that's what I need to compute. So it's trace of 1, negative 1, 0 squared. So this when I square is 1, 1, I compute the sum, it's 2. So this is 2. And the same for alpha 2. Therefore, cosine phi is what? Alpha, so I have negative 1 divided by square root of 2 times square root of 2. Right? So this is square root of 2. So this is alpha 1, alpha 2. and this is -1. We computed it. So it's -1/2. And voila, so therefore it means that phi is what? 2 pi over 3. Which is exactly this angle here. But this computation you can do for SLN as well. Right, Sanchita? So you just take, you had 1, 2, and 3 here, but you can consider all pairs like that, and then H corresponding to epsilon I minus epsilon j will be EII minus EJJ. And then to find alpha IJ with alpha KL, well, you compute trace of corresponding H's with corresponding things. Yeah. And the bunch of them will be zeros. So the answer is like that. It's actually also answer is given in the following matrix. So 2 on diagonals and -1s on subdiagonals. And zeros everywhere else. So roots which are simple, right, corresponding to I and I plus 1 here, gives you -1 as a scalar product. And they are all of the of length 2. Square root of 2. Yes. And then if you take other indices, then the corresponding scalar product will be just 0. So this means that they are in such a, in such a chain, and we will see such pictures. So if they are close together, these two roots, then you have some non-trivial angle, like 2 pi over 3, like in SL3. And then if they are not, relate, well, they're far enough, they're just orthogonal. So that's what's going on for SLN. And this is Cartan matrix for SLN. What's it called? Okay, so this is something from last time. Now let's go with. So in problem 1 for SLN, we would like to see that the Weyl group is SM.
It's just I want to ask because I couldn't finish something, but I cannot finish.
Okay.
So I was thinking in this, and I consider a presentation of this group. So.
Okay. So maybe the same way as you did. Okay.
Like we know that we have some
Generators.
Standard generators, which are given by transposition. So this thing sends the I element to I plus 1. I mean, okay, I and I plus 1, they are interchanged.
Right.
These are transpositions.
And it doesn't change anything else.
Okay, and we have the following relations, which are the square, its identity. If we compute this,
Yeah, sure.
we will have that they commute, but this is commutative if we have this condition. It's like this, or
Greater than 1, I think.
1. Yeah.
Yes.
Okay. And last one, we have something like this. I think it's. Let me write.
It's like braid relations, what's called.
Yeah.
Braiding. Braid, I think.
This is called presentation of this group. This is
In this way, yes, these are called Coxeter relations.
Mhm.
Yeah.
And we have precisely n minus 1 generators.
Mm-hmm.
Okay, and these should be functions that from n elements to n elements. This thing. Okay, so I was trying to see the relation with this, with the S, with our reflections.
Okay. So you were
But,
trying to discover simple reflections.
Yeah, that's what I was doing here.
Okay.
And of course, we have this type of roots,
Mm-hmm.
but we are fixing. We have many of them, a lot
Yes.
of them.
Yes.
But a basis, it will be given by these ones. E n minus 1 minus a e n. So in my computations, I was taking this type of roots. So I have this, and let me see. So I was trying to consider. I was trying to see.
I think what you would like here is actually
the reflection.
E3 minus E4 here, right? And so
Yeah,
on.
yeah.
So roots of this kind, epsilon I minus epsilon I plus
I
1.
plus 1. Yeah.
So these are called simple roots.
Simple roots. Okay. So what I was trying to see, it's trying to assign to each Si associated with one of these roots. I was trying to assign this kind of a permutation. And I was trying to verify these same relations. So we have, of course, we have that Si squared is identity.
Okay.
We have the formulas for this, and geometrically we know that the square is identity.
Yes, yes.
And also I was computing the second part, Si is j. When I was trying to see when it was the case that they commute.
Okay.
And this, I get the same thing, the same property here. And what else?
So you just straight compute both parts in straightforward way, right?
Yeah, I have the computation here, but I will not do it in detail. But the thing is, I want to see construct an isomorphism with this group and the group generated by these reflections, simple reflections. Okay, the thing is, from now I have the same relations, I have the same number of generators because we have n minus 1 simple roots.
Right.
But the thing is, I don't know how to.
Yes.
There's
So
something missing here.
you constructed a homomorphism which is surjective from here to here, right?
Yeah.
Because you checked that all relations here are also relations here.
But,
But maybe here you have more relations.
And there's
Right?
a problem, and the problem is
Yeah.
in this Sn we have that each transposition they are maps from n elements to n elements. And here I need to try to fix this thing for Si because this should be something like that. So I think I need to try to.
You need a set of n elements that it will permute.
And I was trying to set this alpha 1, alpha n minus 1, and then maybe considering the sum of alpha 1 and alpha 2. Like I was trying to, in analogy with SL, that we have alpha 1, alpha 2, this is alpha 1 plus alpha 2. And then when we are computing reflections, we can think that we are permuting n elements. Here are 3 elements, and we are just changing this. So we have permutations.
Yes.
But still, I was trying to.
That's a good idea, right? So you take not R is too much, right? So because you have more than n elements, you need n. but you would like to have simple roots
Yeah.
and act on simple roots. But
Yeah, I was thinking to trying to fix this.
but the simple roots are not enough though, right? So if you have all roots, then you have too much. If you have just simple roots, you have n-1 of them.
Yeah.
So for example, just 2 of them, you still need 3, right? So you need to add something. I think you need to add maybe the root which, like, I never checked this, but just to continue, maybe your thought is, and maybe Sanchita can say something about this. So you have the last one is this one, but sorry, epsilon, right? Epsilon n, like this, but maybe you also would like to have epsilon n minus epsilon 1. So to if I would like to, to have an element, like to continue what you did, I would add this one and try to see that it permutes this. Right.
Yeah, but okay.
But also plus and minus of this. Right? Because, for example, if you consider like just a simple transposition, right? If you consider just simple transposition corresponding to alpha, this will permute this too. And the other one permutes this too. I'm just worrying. No. You should have three of them, so not plus and minus. Yes. So in this case, we added alpha 1 minus alpha 3, right? Remember? So maybe it should be alpha 1 minus alpha n, something like this. Yeah, I think this should work, and if you check on this set, this should work. But there's a more natural way to see this. Yeah. I think if we discuss it, then I think this might be clear why this one should be added. So so Sanchita, would you like to add something?
I think Oshi had a different way.
Okay, so what did you do?
So first we can reconstruct the group as n. It's like some free group generated by n minus 1. Denote this free group with n minus 1 generator.
Okay.
Mode some relations.
Exactly this, right?
And that's
Yes.
the relation is.
Yes.
I got the solution of sigma, and we can, and then we consider the Weyl group of SL. It is also the simple roots generated by the free group generated by simple roots, mode some relation, and first we check this simple roots, the reflection of this simple root satisfies this relation. So we have this relations. And maybe there's
Maybe there are more.
more. Yeah.
Okay.
But it means we have, but this more means this is actually some kind of co-subgroup. It means.
It's a quotient of Sn.
Yes.
Yes.
Yes. And quotient some normal group.
Yes.
And then checks the size of this group and this group.
All right.
And that is where I'm stuck. How
How to
to find the size of this group. Maybe there's no such good way to check the size of Weyl's group.
you can find Weyl chambers here, and Weyl chambers are exactly
The number of Weyl chambers.
yes, and then you can see that you can like either use what we saw today or just see by hands that each so Weyl chambers here are in SLN. Yes, so for SLN we need dimension of E to be n-1, right? And then so we actually consider subspaces in diagonal matrices, traceless diagonal matrices, right? Such that H1 greater or equal than H2. So this is C+. So these are diagonal elements of my matrix. I like this. Okay, so I claim that this is C+. And then any other C is given by the following. H sigma of 1, H sigma of 2, and so on. H sigma of n, where sigma is some permutation, sigma for some sigma in Sn. You can see this can be done by hands, just but you have at least, and the different permutations give you different, of course, Weyl chambers, because you just interchange like Hi and cannot be greater than Hj and less than Hj at the same time. So all permutations give you different Weyl chambers. So you have at least number of. Wait. Yes, maybe that's not very good because it gives you a wrong estimate, right? From it gives you estimate. Right. But which way? So then order of W I'm saying is greater than n factorial. And I need it to be smaller. That's what I need, right? I need this, but not this. So maybe with Weyl chambers doesn't work so well. Well, there's another statement, I don't know if we will cover this or not, is that actually action on Weyl chambers is simply transitive. It means that for each and maybe it also can be checked by hand for SLN. Simply transitive means that if I have one Weyl chamber and another Weyl chamber, I can have an element that connects them, but this element is also unique. Okay, and if I know this, then it is true. If I know this, then I know that W is exactly n factorial if I know Weyl chambers for SLN. Then what you did is kind of, yes, I think that's the only way to finish the gap. But let me say something. There's a natural way how to see that these are permutations. I would like to go from, I would like to consider an action of Weyl group on D star, not H but D star. So let me erase something. So I would like to have D, again, it is diagonal, all diagonal matrices. And inside you have H which is traceless diagonal. So your S alpha I, right, where alpha I is epsilon, so your simple roots, right, epsilon alpha. So simple roots we already covered, actually, right? So, so anyway, so you have alpha I is this. Actually, maybe we can take any roots. Any roots. Without any knowledge of today's lecture, we can still do this. So, like this. It actually acts on H star, right? That's from general theory. But it actually, H star is some subspace in D star, right? So actually I have H star inside D star. So on pictures, what's going on? So you have H star, and you have this is so this is H star, and the whole space is D star. So of course I have like a reflect. So if I have a root, right, I reflect with respect to some plane in H star, right? But what I do, I actually take, so this plane in our picture is a line. So I actually consider some hyperplane in D star, right? So maybe I should put it like this, which is orthogonal to H star, right? And it actually intersects H star in the hyperplane L alpha, which is orthogonal to alpha, right? So, I define action, so this is like the big space is D star. I define an action of S alpha J on D star as a reflection with respect to this bigger plane, right? And D star is actually, that's what I meant like by adding this one additional thing, right? D star is actually Rn. And I claim that S alpha J acts by permuting coordinates. And this can be checked in a straightforward way. So let's do this, maybe. Again, so what I mean is this. So let's do this. So first, to have this equality, I need some good basis, right, for D star. This good basis we know, it's epsilons, right? So this epsilon i's is a basis for D star. And so if I take some element f in D star, then this is just A1 epsilon 1 plus A2. So F is this, A2 epsilon 2 plus and so on. And so therefore I consider F to be a vector with coordinates A1, AN in Rn. Okay, but then I have Right. Then I can define if I have an element in D star, right? So what is the inner product that I have in D star? All right. So I on H star I have a trace. Well, so trace on H gives me an inner product, right? So let me write it like this. Trace on H gives me inner product on H star. But here I can replace H and H star by D and D star, because on D it's still non-degenerate. Okay? So the same trace on D gives me inner product on D star. And if I restrict to H star, I am still, so restriction respects the Euclidean structure that I already had, right? So I actually expand from this plane to the whole D star. And then trace, so then if I have two elements, F and G, right? This one corresponds to some vector A, A1, AN. This one corresponds to some other vector, B1, Bn. Right? So this is then H A1 epsilon 1 plus, so I need to compute trace of this, H1 epsilon 1 plus so on plus AN epsilon n times H B1 epsilon 1 plus so on Bn epsilon n. So this is just by definition what it means to compute, so what this parenthesis is on D star. But then if I compute this will give me exactly scalar product of vector A times B. So in this basis, under this identification, the inner product that I had in my abstract thing is exactly just a scalar product of two vectors. Okay? So now let me compute how S alpha J acts on D star. So S, first of all, alpha ij corresponds to which vector? Yes, but in this form. It's 0, 0, and then 1, and negative 1. This is on ith place. This is on jth place. Right? So this corresponds to Rn. Right? Just to compute the scalar products that we understand. Right? Just dot product. It is called dot product in English. Right? All right. So, and here, like 0 again. So what I would like to do, I would like to take S alpha ij and apply it to some vector A. So by definition, it's A minus twice A alpha ij over alpha ij. So this is actually 2, right? So this cancels. Times something, alpha ij. Okay, I claim that, okay, I have to write A1 so on AN minus, so what's the scalar product? This scalar product, I will have, I'm sorry, Well, first of all, my alpha ij is this, 1, -1, right? But this scalar product is exactly ai minus aj times ai minus aj. So what this minus this is exactly, it's not square, it's this too, right? It's this vector with I and j replaced. Right, so it's a1 and then I, a, j, and ai, an. And this is on ith place, and this is on jth place. So this is j, and this is I. So you just see explicitly that you take A and the action just interchanges. But for that, you should go from H star to bigger space. So actually, you're working on some subspace, and you cannot see this like naturally. But on D star, you see that immediately. So that's how it.
Excuse me, so
Yes.
what I did was, I tried the same thing. I just used the metrics that you wrote before, kind of cut out the metrics for the trace metrics, and then just try to use the relations that we had for
Yes, yes, yeah, I understand. But the question here, non-trivial, is that how you prove that there are no more relations in W. And this is what we discussed when O was showing. Yeah, so we need the size. We need to say something about size, and this is like a non-trivial thing. Yes. The most, I think, what comes to my mind, the only way to say something about size is to count Weyl chambers, but for that you need to understand what are Weyl chambers, and this is not in the scope of last time lecture. So now we know, right? Yeah. Okay, very well.
Yeah, so we should prove that first part, it will be like this. C is isomorphic to G, and okay, I didn't explain. I wanted to consider transformation phi. It's goes to from SO to n plus 1, C to G.
Can you remind what was the definition of G?
Yeah, one second. I remember how Luke is polynomial is here. N, 0, 0, 0, 0, 1. I forgot to put it here.
Yeah, so maybe, right? So we can continue. So it was x and GL 2n plus 1 such that bx is negative xtb. Or maybe some other form. This is what's going on. It's this, I think what's written there is x plus b inverse xt, b is 0. It's the same as this.
Okay, so so I consider this map, and I need to prove that. Okay, first I need to show that it's a linear transformation. I don't know. Do I need to I just need to consider x1 and x2 from SO plus 1C and any alpha beta from C. And prove that alpha x1 plus beta x2. Oops, sorry, I forgot to say that how works this map. It's
Okay.
y, it will be phi of x, such that y is bracket plus b. That's our B matrix.
Okay.
So,
So maybe, I don't know.
okay, so first step is just
I didn't, so I didn't have any explicit in mind. But I think it is
directly multiplication of B.
yes. Okay, so we just need to check. So first of all, y. If I take x from where to where? It is from SO to G.
Yeah.
So if you take y from SO, then if you take x from SO, then y should be in G, right?
Yeah.
Let's first check.
Yeah, it will be.
But why you have two elements, x1 and x2 there?
I just wanted to prove that it's a linear transformation.
It's obvious.
It's
I
obvious.
think.
Okay, yeah. That's what I want to say. Okay, yeah, and then I need to prove that it's injective and projective. Yeah.
First, you need to prove at least that you went in G. That if you take x from SO, then you get an element from G, right?
Okay. But oh, 1 second. Okay. I think I just did step 2.
Does anybody else have the same transformation?
Maybe it's, I think it was.
But you can prove that it's in that place, but it was
Do you know how to prove that? How to show?
that if you take one in G, you have it in SO to N.
The other way.
Ah,
So
the
what
other way.
Christina is saying, it's the other way around.
It's because when you multiply, because B to square, it's the identity.
Okay.
So you have the SO to N plus 1, it's all matrices skew-symmetric.
Yes.
So it's the definition of G in that first line. So when you multiply by B, but only from one side, as I think, you will get the property.
Yes, but here you have a commutator.
Yeah, that's the thing, that you can only take it from one side. But I think if you multiply from the other side, it's also true, because when you take the transposition, you will get similar.
Okay, maybe we can check actually.
Just check the example.
If you take bx, right, you would like to have this. No, so for y you would like to have this. So I need to check that b y is negative y transpose b. So bx is negative y x transposed b transposed b, right? So b times b is 1, right? So this is 1. B transposed is b again. So this is also 1. So x equals negative xt. That's good. Now, if I take y equals from the other side, right? I need to check. So if I take and multiply
From the other side.
b from the other side, yes? So I need to check that yb is negative byt, right?
No,
It's the same as this. if I multiply from
No,
the right,
you want to check that it's in G, so you have to multiply from the left.
I'm sorry. So for y, I would like to see this, right? So maybe. So let's try to. If I just plug in, I will have bxb equals negative b transposed, which is b itself, x transposed b, right? So if I multiply by b, so that's it.
Yeah.
That's it. Yes. So this is we checked. Okay. Okay. Let's continue.
Okay, what I introduce. One second, I'm not sure now. Okay, I don't believe. Okay, here I just wrote that that's the whole, that's linear. And second step was to prove that it's injective, like actually that phi is bijective, the two steps, as it's injective. Okay. And for that, I assume for that we have phi x1 equals to phi x2 for just random for some x1, x2 from C, and I need to prove that x1 equals to x2. Okay. So for that, from this, it goes that x1b equals to x2b commutated. And if we will multiply its b is symmetric and invertible, so we can multiply from the left and from the right. And we can get that that's this. Okay, let's write like this. dx1b
Yeah. So if x1 and x2 were not from SO, then of course the injectivity were not true because we would just add b, for example. If I have some x like that, then if x with b and x plus b with b is the same thing, right?
If you have one.
Yeah. So I'm claiming that if we had we didn't have this condition, then of course we had no injectivity, right? Because we could have something like this, but still x1 not equal to x2. For example, x1 is x2 plus b. But b is not in SO to n plus 1, for sure. It's symmetric, but not antisymmetric. But still, it doesn't say anything because.
But you cannot have x1 to b because it's not this.
Yeah. So you cannot have. Yeah. Anyway, so your Okay, so how do you check this?
And I just wrote, because B is, it has two blocks, these two blocks, so if I hope that I did correct, I got this, it's just 0, and I'm not sure what's this, it should be x1 minus x2, 0, x minus x2, 0, 0, and another 0. Yeah, and
Okay,
then,
so that's how you. If it's 0, then x1 equals x2, right?
yeah, because it should be they must be skew symmetric, and also our algebra is simple, yeah, so it cannot have trivial idea.
How we get this formula? How we get this formula?
I just multiplied this from the left and from the right b. Yeah, and there is some calculation that I skipped. I don't know.
Okay, so this is some calculation.
Yeah. I hope they correct, because from this I got this, like how it
I think
explicitly looks like.
if you multiply your that from the left and from right, you get your this equation right hand side is 0, right?
Yeah.
I think you actually moved.
One second. Yeah, it was 0. Yeah,
So you have x1 b minus px1, right? Minus x2 b plus bx2. Right, if you multiply, so this equals to 0. If you multiply by b from the right, from the left, I don't know, you'll have bx1b minus bx2b, what you have there, should not be 0.
But I did it a little, firstly multiply from the left, from the right,
Minus
and then
x1 plus x2 should be 0. So maybe if you compute this, then you will get something like this. I don't know. But that's the only way, I think.
No, but it's a little different because you just one second.
Well, okay. So suppose this is injective, and you can somehow check this. But this also should be homomorphism of Lie algebras, right?
Yeah,
And this is just follows from the fact that if you have a group, right, then e to the b, a e to the negative b is a homomorphism of Lie groups, right? And differential of this homomorphism gives you this homomorphism of Lie algebras. So that's why this is a homomorphism of Lie algebras. So also
We should also check one more thing.
yes.
The dimension is the same. I mean, the dimension of S is since she used the argument that if a linear map.
It's a linear map, and then Christina proves that it's injective, right?
And she wanted to prove that it's
Surjective, right?
You check the dimension is the same.
Yes, you need to check the dimensions the same.
I didn't check. I just checked
Okay.
the easiest. Yeah, also that's preserved for Lie bracket, and I was pretty
Okay.
happy.
Okay.
But that's preserved for Lie bracket. It's also easy.
Yes.
But yeah, I did
There's
check
actually
about the image.
what Jacobi identity.
Yeah, yeah.
Okay, yeah.
That's all.
Very well. But okay, what about root part? Maybe you can just list the roots that you have.
Hold on a second.
So you need to check that diagonal matrices inside G gives you Cartan subalgebra and find corresponding root system, right?
Yeah, and I did that to prove that it's Cartan subalgebra. I proved that. 1 second. That it's a maximal abelian subalgebra, and that every root we can rewrite as the sum of
So you're checking that it's maximal Toral subalgebra, right?
okay.
So it's each element is diagonal. Well, it's diagonalizable, of course.
Yeah.
So it's Toral. It's obvious, right?
Yeah. So I okay. So I can claim that H is okay diagonal. Like this. H1, H2. And
so diagonal matrices inside SO, inside G, they look exactly like this, right?
yeah, and then I
I think maybe the two n plus
Yes.
one symmetry.
Yes, you have two n elements, and what's the last one?
yeah, 0 in the end. Okay, and then I claim that our like H is in diagonal is a diagonal matrix in D. So and our D will look like every D element is a sum of HI. This.
Yes.
See that? Так, okay, and
So what is D capital?
так, the capital is
What is J?
what is J? No, J is this J.
Yes.
It's that's EIJ is just matrix with
Yes,
One
well,
with, like,
I understand, but you don't have, on the other side of your equality, you don't have any J. You have sum over I only.
Oh,
yeah. Wait. Sorry. It's I. Yeah. Yeah, it's I.
Okay. So any diagonal matrix can be written like this. I agree.
Yeah, 1 second.
Mhm.
Okay, and then
Then you just need the basis for G.
yeah, and I calculate
And then you just check that this basis is an eigenbasis for each element from H. Yes, right? Because and you consider add H, apply to each element of your basis, the good basis that you need to find. And this will give you some number. Right? Okay, so just say what you wanted to say. Let me not confuse you. Okay.
I got just that my alpha ij is actually hi minus hj. This count as number?
So h is are some numbers.
Yeah.
Alpha ij, what it is alpha ij? It's another number.
It's, no, it's root.
Okay, root should be an element of h star. So I think it's like that, right? Alpha ij acting on this, right? Gives you this. Okay, this is the same as we had with SLN, right?
Yeah.
H is, and this is ij is from 1 to with this n, right?
Oh, yeah.
Okay. So far you have not a lot of roots, right?
I don't know. Like
Well, if you
I
compute
think-
dimension that you get, yeah, you should have more.
I did something also.
Hmm?
I did it.
Okay, so maybe let Abner help with this. Okay, well, you showed us the part with isomorphism and something with roots. Okay, so let's continue.
Okay, so we want to check that first it was diagonals, but in G. So if we want diagonals that it stands this, we need diagonals like that, like with the first n elements be the same, but with negative sign. Equal last n elements. And 0 in the.
Yeah, so exactly what is written here. Okay.
So I think to check that it's Cartan subalgebra, what I did was to map both by b, just multiply by b, the diagonal, and we will get some matrices that look like 0, and here like a diagonal of x to n. Like we can say lambda x minus lambda x and 0 in the rest. And we have to check that this is a Cartan subalgebra, and these elements only commute with elements like this. Maybe we can skip that.
Okay.
It is. And then we have the same base for the dual space. It's like in SLN that you say.
Okay.
It's,
So you have epsilon i's. So suppose let's okay.
so we have.
Yeah. So you would like to write roots in terms of epsilon i's.
And yeah,
Okay.
roots and subspace like
Okay.
the G lambda.
Yes. Yes.
G
Very
alphas.
good. Okay. Let's do this.
The alphas, and we will have EI, where EI, as we remind, is add on. Okay. We will get lambda. Okay, and we have EI and minus EI, EI minus EJ.
Right.
Every time it's for I different j when they appear in operations. And EI plus EJ
Yes.
minus EI minus EJ, and the subspace, this subspace will look like this. One, n plus I. This one is n plus I. 2n plus 1 minus e. 2n plus 1 I. And this one, it's j. Plus n, comma, I plus n. The next one, it's j plus n minus j, comma, I plus n.
So actually you have I here runs, so as written here, you can run from 1 to n plus 1, but here you need to only at least until n, right? Because after n, you have something that dependent on the first part. There's one important observation. And how do you compute it actually? So
It's 6, I think.
there are 6, but here he didn't tell us if I is greater than j or j is greater than I. So you have 2 sitting here. Yes. So
Yeah, it's like when we do that thing with SLN, SL2, SLN, I don't know, it was SLN that you have to take this and operate them in the diagonals and check which eigenvector you get.
yes.
And,
So you actually, right, you take, for example, this element and compute it with this element. You see that, for example, if you compute this with this, then you will get xi times this element. Right? So this is just some computation. So it means that this is a root with corresponding, this is a root subspace corresponding to the root like this. So if you take, for example, this one and commute with this one, what you will get is negative xi, negative xj. Right?
so they related that these are
Yes.
bases of
Times again, times this. Right.
It's our basis. I can
So, and by the way, this is the basis for G. How you can see this? You actually just see that.
bases.
Yeah, you see that G has some block form, right? So you what are the blocks?
Because yeah, the basis in SO to N it's ej minus e ji, and you map with e, and then you check how is the basis there.
Yes, but like if you just look at matrices that correspond that satisfy this.
Yes, it should have no problem.
Yes, so it will be, I don't know.
Yes, that's great.
You can write down what is the form, and then each of these is just you just looking at this block form, right? You see that this should be exactly the basis, and then when you check for each element of the basis, it actually an eigenvector for an adjoint action of this. You just check it, and that's how you do this.
D and B is symmetric.
Yes. So, for example,
A is GL.
yes, for
A is GL.
You will only
Yes,
change
yes, yes.
lines like ABC with the minus E transpose S, because that's what B does.
yes. So, for example, we can take E.
Yeah, I think it's some use for
Right.
further. That's involved.
So maybe you can take some basis here, some element here, and see that it is actually an element in here, right?
Yes, we can take some, like, because our rules system, the Cartan sub algebra looks like always like
Thank you very much.
these matrix here and minus same thing here and 0.
Yes.
So we can always take a set of basis of this thing is like hi minus hi. So the hi is the
EII.
N-dimensional eigenvector.
is the just write it.
Yes.
And it's I minus 1 minus 1.
Yes. Mm-hmm.
So we know that. Can we read here?
but maybe you don't need -1 anywhere. In HI, you already have, so maybe HI is without.
Is this right?
No. This is correct. I'm claiming that you have in HI just one. You don't need this. Just have one here and -1 in the next block. So exactly, for example, you have x1 here and -x1 in the next block.
Okay, it doesn't influence the next.
Of course, you can take 1 and -1, but this gives you less vectors than you need.
So, if we consider the commutator of this guy and this guy, we will have some useful formula. Commutator of this HI,
Mm-hmm.
it will be first commutator of
Mm-hmm.
and anti-commutator.
Oh wow. Okay.
With
Just a fancy notation.
and direct product is with C. And
Mm-hmm.
same thing for F minus anti-commutator of
Mm-hmm.
capital H, HI with D. And maybe
Minus, I think. I think also minus in the left bottom entry. Minus FT HI. Yes.
So from this we can just separately compute each part.
Mm-hmm.
Yeah, we can get what is the root system of, because we can always choose the basis of this G. Like we take if we fix some basis of A,
Mm-hmm.
and we take the DC, BC, D, F, G is 0, and then
Yes.
have some basis of subset of basis of the whole G.
Mm-hmm.
And do the same thing for B, C, D. Then we get what is the root system of the whole algebra. So the answer is maybe is enough, or I can.
Yeah, I think it's enough. Yeah. But also, what this is useful. But also, I wanted to say that if you just take why this is a basis. Because you look at this block form,
Yes.
right? So suppose I take Eij, where I from 1 to n and j from 1 to n. So it means that I take an element from A, but from this block form, I also should have negative this transposed, the corresponding element in this, right? So that's exactly what's written here, Eij. Then I add n, so I get to the next block. And I transpose j and I. So this is naturally a basis element because I have this block form A negative A transpose here. For example, and you can just find that this is the basis in here, just looking at this block form, and then it just commute with this thing. And get corresponding root vectors. That's it. And this is of course also a good way to think about this in blocks, right? Yes, very good. by the way, right, for if n equals 2, what we get?
B2.
We get B2, right? Because we have 2 means that I and j can run from 1 to 2, right? So I have E1, E2, then E1 plus minus E2, and plus minus of all this. Right? So this is exactly the picture like this. So this is E1, E2. Then I have E1 plus E2. And then I have E1 minus E2. So these are all positive roots. And therefore, and you just add all negative of them. And this is your system B2. So now you know that B2 corresponds to SO5. A2 corresponds to SL3. A1 union A1 corresponds to what? SL2 plus SL2. And the last one is very hard. It's an exception. What's called exceptional algebra, not a classical one. It's like G2. And okay, this is the last problem. If somebody got to this problem, this is how you construct one of the ways to construct G2. Yes. Okay. So do we have more time? No. Okay. So let's stop. Thank you, everybody.